Hello everyone, my name is Juliette Delbrel and I'm a second year PhD student at the University of Manchester. I will be presenting my work on the Kilauea 2020 to 2021 eruption and comparing satellite and ground-based measurements. A special thanks to the folks over at the Hawaii Volcano Observatory, especially Tamara Elias and Trisha Nadal for their input. Kilauea is the youngest volcano in Hawaii, located on the youngest island. It is situated on the flanks of Mauna Loa, the largest volcano on Earth. It erupted around this time last year, from 20th December 2020 to 13th May 2021, with SO2 plumes dispersing mostly towards the communities of Pahala, Ocean View, and the Kona Coast, which received a couple of health warnings throughout the eruption. This is not surprising, as they are communities downwind of the volcano. This eruption was interesting as it was a low-lying, mostly grounded plume, which is difficult to detect and quantify via satellite, so this was a great opportunity to test the robustness of tropomy and plume Traj by comparing the results to ground measurements. What is so great about Kilauea is that it is one of the most well-monitored volcanoes in the world, so we know that the data that we are getting is reliable to some degree. This work focused on comparing the results to look for any discrepancy and determine the efficacy of tropomy and our analysis toolkit plume Traj to measure low-lying, mostly grounded plumes. The ground measurements were operated by the folks over at the Hawaii Volcano Observatory. The instrument used was a mobile DOAS mounted on a car. The plume speed was assumed to be the wind speed, as the plume mixes with the ambient air relatively quickly for an effusive eruption, so the wind speed was measured using an anemometer also on board the car. SO2 cross-sections were done approximately every 10 minutes, between 4 to 8 times, and the wind speeds were measured at the same time. The two were multiplied to get the flux, and an average was taken. As for the satellite data, the tropospheric monitoring instrument measured SO2 vertical column densities, and plume Traj calculated the flux with the help of high split. The wind speeds were modeled by the global forecast system. Plume Traj is an analysis toolkit combining tropomy data with back trajectory analysis using the high split model to produce individual pixels measuring altitude, and injection time. The back trajectory model, in this case high split, traces the path of the air using global weather model to track back the location of each pixel and hopefully back to the volcano. We pick particular points and we have a variety of starting heights. We have the volcano and the tropomy pixel, and we have various options. The different trajectories move at different speeds and directions due to the wind shear in the atmosphere. The idea is that only one of those trajectories will go over the volcano. The trajectory that crosses the volcano, or gets closest to it, is the chosen altitude. The vertical column density is measured by dividing the slant column density by the air mass factor. The air mass factor, or AMF, depends on on atmospheric properties. From this, we can calculate the mass of each pixel. If we have the measurement time and the time it took for the pixel to travel back to the source, and we subtract one from the other, we get the injection time. And then if we combine the corrected mass by the injection time for each of those pixels, then we can get an SO2 flux time series, which is what we're trying to get. So here is shown the SO2 flux for the ground measurements in green and the satellite-based measurements in blue. You can see a clear discrepancy between the two. However, we thought that the average SO2 flux from tropomy might not be representative for this particular case. This is because we knew that we were missing a lot of the plume due to its proximity to the ground, especially when the topography is highly variable. Plume Traj outputs one flux for each hour, so the average flux plotted here in blue is the average of these 24 hours. The maximum flux just selects the maximum flux reached for each day and plots that instead. So this is what we've done here. The yellow line represents the maximum SO2 flux. Unsurprisingly, the flux increases throughout, but the ground and satellite measurements still don't match. We could tell that the trend was the same: high in emissions at the start of the eruption, followed by a plateau in emissions approximately 1 week later. It then occurred to us that the ground and satellite measurements were not using the same plume speeds. So we decided to compare them. The ground measurements use an anemometer, whereas plume Traj takes in global forecast system wind speeds within high split, as mentioned before. From this graph, you can see that the anemometer wind speeds are almost always higher than GFS wind speeds. This was good news, and it was telling us that perhaps the wind speeds were what was causing this big difference in fluxes. So we decided to take the ground measured fluxes, divide them by the anemometer wind speeds, and multiply that by the GFS wind speeds instead. If the fluxes matched, the tropomy results, then it would be telling us that the ground and satellite fluxes agreed. This is what our results showed, the purple triangles. We could see a reduction in SO2 flux, and you could definitely agree that they agree within, that they agree within the error bar of the triangles. There is still a discrepancy at the first points, but the very first point on the 21st December 2020 has 2 orbits, which means that the plume is cut in half. This underestimates the flux each time. For the second point on the 22nd December, half of the plume is completely covered by cloud cover, which masks the signal. And I will talk about this a bit more now. So in the figure on the left, you can see meteorological cloud in blue where the plume is. And when you compare that with the SO2 corrected VCD, which is what determines your concentration and hence your flux on the right figure, you can see the VCD is much smaller where it coincides with high cloud cover. Now you could argue that this is a coincidence, but this is actually a recurrent problem throughout this eruption and in fact in other eruptions. Now why do we care? Well, meteorological clouds located above the plume mask the signal, which underestimates the VCD and hence your flux. This could also be contributing to the low SO2 fluxes we are getting when taking the average, and even possibly with the maximum flux as well. The fact that the plume is located near the ground means that it is located underneath meteorological clouds. Unfortunately for us, the overpass tends to occur around the same time as the clouds settle in over Hawaii, meaning around 1 p.m. local time. There is a good correlation between satellite and grounded plume measurements when using plume Traj to measure the flux. The wind speed measurement is important when measuring the flux because that will definitely be impacting the resultant flux. We came to this conclusion by comparing the satellite and ground-based measurements for a low-lying plume at Kilauea. There could definitely be other things at play affecting your flux and impacting its accuracy. One of these is cloud cover, which can mask the SO2 signal and underestimate the satellite measurements. Thank you for listening.